Good afternoon. Welcome to the Veriest online meeting. Play a short video. So good afternoon. My name is Moshe Salzberg. I hope you can see and hear me. I'm the CEO of Veriest, and I would like to welcome you to the first online meeting that we are having. Just very quickly, Veriest is a ASIC engineering services company that has been around for more than 10 years, headquartered in Israel with 4 sites in Serbia and Hungary. We are about 100 engineers working in different areas of verification, design, and etc., and software, and FPGA design and IP design. We do believe in knowledge sharing, and that's why we are having this meetup today. We have been doing some 5, maybe even more meetups in the different countries that we operate over the last couple of years. And we use every opportunity to present conference papers in different conferences. I think generally speaking, today, if I may say a few words about what's going on today in the world, is that during this coronavirus crisis, we see a lot of countries kind of going inside. We are all inside our own homes, and each country is kind of spending time with internal issues and not international issues. Having said that, we see a lot of knowledge sharing in the coronavirus crisis as well. You know, we see doctors coming from different places to help people. We see people sharing knowledge about how to treat. We see people, companies actually sharing, making open source of their plans and projects, how to generate or how to create different machines that can help ventilators and etc., etc. So even in the situation that every country cares about itself, which is natural, we see a lot of knowledge sharing, which is important. Because I think that, you know, one aspect of the crisis that we are going through is that, in spite of the fact that each country is taking care of its own, we are all in the same problem. We all need to help each other to get out of it. So that's true for the Corona story. I think it's true for our industry as well, and I'm very happy that, you know, once we announced this online meetup, we have about 200 people that registered. You know, I still don't know at the moment. We have about 107 people attending, but we had 200 people that attended that registered from 16 different countries, which is great. You know, it's in Israel, in Europe, in the US, India, Singapore, Egypt. So it's great that we can share knowledge. Each one of us, I guess, that from the safety of our homes, but we can share knowledge and be together in such a situation. So I think it's great. We wanted this meetup to be not really a platform to exchange ideas. That's why we chose actually the Zoom platform. That's the first time we're doing that, so we'll see how well it works. But we wanted to make sure that that we can find a way to exchange ideas even if we are in a very big team, which is great. I want to say a few words about Zoom before we move on. So, if there are people that are not familiar, I think that not many people are unfamiliar with Zoom these days. But a few words. First of all, if you have such a screen, you can press on the speaker view and you'll see just the speaker and not everyone else on the line. Also, you have the two commands here to unmute yourself and to show video. And especially in the Q&A session, I will be very happy if people can show themselves on the video so we can actually have a human interaction as much as possible. At this stage, I have muted all of you, and during the presentations, we're gonna be muted everyone, but eventually in the Q&A session, we're gonna open for people to speak up so we can have a human interaction. Once you pressed on speaker view, you should see the viewer, or the speaker in a big screen. Now you're not seeing that because actually we have a presentation going on as well. So you should see me on the side of the presentation. Something else that I wanted you to know is that, and this is from another presentation, but here you can see the number of participants. In our case, we are at 114 at the moment. Once you click on participants, you get the list of the participants here. You can ask to be unmuted, or you can raise your hand. And then the control room can open your mic. You can also press on chat and ask questions to the speaker. Actually talk to one of your colleagues on the call as well, or to the team in general, or contribute something. Again, we wanted this to be as interactive as possible during the circumstances. As I mentioned, another thing that I want to share is that you will have the presentation and the speaker. You can move this bar here to increase the size of the presentation or the speaker as you wish. During this presentation, during the session, we'll be using this feature of Zoom called polling. So we'll be asking you after each presentation, how did you like the presentation? So after Elihai's presentation, the first presentation, the second presentation, you'll be asking that. I hope it works. Not always it works with Zoom, but I hope it works. And then we can get some instant feedback from you about the different presentations. We'll also be asking you about attending future meetups. And if you're interested in speaking in a future meetup, please contact us at meetup@veriest.com so we can consider you for a future session as well. With that, I want to handle to Elihai to speak about an hybrid verification approach for embedded processor integration. We're going to have a 20-minute presentation. During the presentation, feel free to ask questions on the Zoom chat that Elihai may be able to address. And after the two presentations, we're going to have a Q&A session that you can actually speak up and ask questions in your voice. Use the raise hand feature to ask for your turn to speak, and then we can have a direct conversation. Let me introduce Elihai. Elihai is the verification technical leader of the Intel Emerging Growth Incubator team in Israel. In this role, he directs the team's verification methodology in all aspects, defining UVM architecture structures and best practices, integrating new tools, developing common verification components for efficient reuse across projects. In addition, Elihai is the verification manager for several FPGA and AC clusters, leading teams both on site and abroad. Elihai is drawing from his experience at Intel, Broadcom, and Qualcomm, among other companies. And Elihai has written and presented several technical papers in conferences and meetups describing advanced verification methods and project-proven best practices. With that, I'm going to stop sharing, and Elihai, I'm going to pass it to you. Just a second for you to bring your, let me unmute you. And so are you unmuted? Can we hear you?
Can you hear me?
Yeah, great.
I cannot share.
So now you can. Go ahead and share.
Okay, great. Okay, can you see my screen?
Yes.
Okay, great. So thank you for asking me to speak in this unique event. What I'm going to talk about is based on work we did on several of our previous projects in the Intel recent group. Sorry? Okay, so I'll talk about a few words about embedded processor, what its general task, and what verification perspective regarding this embedded processor. Wait a second. I'm going to talk about the two challenges we had. First of all, is the first one will be the multiple integration tests needed. When you have an embedded processor, usually you override his main interfaces like HB or XI, and you put a BFM there. But at some point before the tape out, you won't go to tape out with only BFM. So at some point you integrate the full RTL of the processor, and you want to run real C codes with the simulation. The problem is when the C codes, development of the C code is manual, well, usually for our case in the past, and I will show a nice way to do it more automatically. The second challenge we had is while you develop the C code, normally you don't need the first part of the simulation. That means bring up the chip and configure all the PLLs, just to check the main interfaces for the CPU. So I'm going to show some hybrid simulation approach to use both BFM and processor in the same simulation. Okay, so a bit about myself: married plus 3 children. It's more relevant these days when we are all here in the living room shouting and trying to walk. I'm doing verification for the last about 12 years. Started with Provigent, then Broadcom, Qualcomm, and then Intel. I really like to code. Amongst my hobbies, you can find UVM and System Verilog. So this is why every year I try to present at least one time in a technical conference. Okay, a bit about my department. It was called one part of the department called RealSense. RealSense is a trademark for Intel. We develop 3D cameras based on laser and other technologies that give the computer ability to see the scene and to analyze it. During the last year, our group started to develop also 3D cameras also for the automotive arena. So, and joint venture with another big groups in Intel. So you'll probably hear more about this in the future. Okay, embedded processor. Each system on chip usually we have at least one embedded processor. It can be ARM or ARC or some kind of or any other vendor type. The processor tasks can be very simple, like register configuration or just PLL configuration and bring up for the chip. And it can be very complex, like algorithms and DSP and matrix calculations. So it varies in this area. As for verification, I did several times verification of the integration of the processor. Because we don't develop the processor, the processor itself, we just take it ready from the vendor. So in most simulation, we leave the processor in reset. We take over the main interface, the master. Let's say if it's an HB, we take over the HB master with a BFM, VIP of HB, and then we handle all the transaction via the BFM. And all this time, the processor resides in reset, and it doesn't consume simulation time and clocks. And it makes us easy to have random scenarios and quickly develop and verify the rest of the chip, but the processor. The main drawback here is actually the real processor behavior is not simulated at this part of the verification. So we cannot really go to RTL freeze or go to the next steps, the final steps of the project with this approach. So at some point we release this interface and we compose a real C code or assembler code that are loaded to the CPU memories and activate, and we take the processor out of reset and out of halt, and we actually check the real processor, how it integrates with the other parts of the chip. The issue here is that for many integration many integration interfaces, the number of tests can be big and big, and also all the tests are usually maintained manually, and it usually doesn't have it have no randoms inside them. So this is the second drawback of this approach. Okay, so what we had till we developed this method. So we just how we run C code, for example. So we compose the main.c, we take ready from the firmware team. We compile it and generate the hexa file, usually using elf2x. And then during the reset phase of the simulation, we load this ready code to the processor memories. And then the processor getting out of reset and out of halt and start executing the real C code. The first challenge is, like I said before, we can have many interfaces for the processor, and many type of scenarios we want to check how the processor integrates with the chip, with the rest of the chip. So the number of tests can be high and high, and the complexity of the tests can be high and high. So what we propose here is to use our already environment test bench that already contains state-of-the-art constraint random verification environment. We will use it to generate random content for the C test, and then run this randomized C content with the processor. I'll demonstrate now. So the first part will be to generate with System Verilog, in our case, to generate some random scenario. It can be very, very big that normally we won't type test of thousands of lines, but if you generate it automatically with System Verilog, it won't be an issue. So here we can see a few arrays of scenario, of priority in delays. that can be just randomized and create thousands of lines of a single scenario that can use as stress scenario for the system, for the SOC. The second part is to translate this part that was randomized, to translate it to C code. This we just do file open, and then command by command we print the lines to the C code. The resulted C code can be very long, not something we can manually write or want to write. Next step is to compile this new C code and generate the hexa file for this code, and of course to load it to the memories of the CPU. Now we have what we have achieved at this point. We have a random content for C or assembler code that is created before the simulation started and will run over the CPU real RTL. So first of all, we have each seed of the simulation, we have different scenario according to the constraints. Second of all, we can use this method also to create a random code on the fly while the system the processor is still at halt mode or reset mode according to the system structure, and then create the content. It doesn't have to be at the start of the world. This is what I want to say. It can be during the simulation. We create the C code and then compile it and load it to the memory, to the CPU memory. The second challenge is that usually the first part of the SOC, when it brings up on real life, we have the boot flow. So it wait for log for the PLL, configure all the blocks, changing all the relevant registers according to the setups, applying all the straps, the strap configuration to the system. This whole part is in real life will be coded in C, but at this point, at the early stages of the verification, we don't have this code, and we don't want to waste time writing it because it will be the part that will be written by the firmware team. So we want to skip this part. We have this part in system Verilog. It's randomized, of course, and using the BFM, but we don't have it in C. So the solution here will be to take a hybrid integration flow. So the hybrid, I mean that the first part of the boot of the init flow of the simulation will be executed by the BFM, by the interface we see here, the yellow one. Let's say it's a HB interface, like we said before. So we have thousands of transactions, HB transactions that were randomized and according to the constraint of the system are executing via the BFM. During this time, the processor is out of reset, but it's waiting on halt mode, and the program counter, the PC, is not advancing. And then the second part of the simulation, we signal to the processor to start running. Pay attention that at this stage, the system is at the point we wanted it. It's after boot, and it's all the relevant blocks are operating. And just now we kick in the CPU with the ready C code that was generated, and the C code is starting to run. So this is the hybrid flow. Just to a little sketch here. So we see here while the LCP stall is 1, so the control over the H address of the processor, it will come from the interface of the BFM. As soon as this is the simple assign from Verilog, as soon as the LCP stall deasserted, immediately this line will drive Z to the lines, and actually what it means that the H address from the processor itself can win over the line and the processor can run its own transactions. So to summarize it all, first I want to say, even if you don't have a processor and just you have some other kind of parts of the SOC you have that you have BFM for it. So you can, this is the idea, you can mix the BFM and the real RTL of this block together in the simulation. This is the main idea. It doesn't have to be embedded processor, but so what we achieved here in these two methods, we have the ability to eliminate the need to write in multiple integration code and the length of it by generating random content for the C, and then use this random content during the simulation. The other achievement here is, in order to bypass the need to write the boot flow and the initialization flow for the processor, for the SOC, like we said before, we are doing this part with the BFM, and then when the system is after the bring up, we kick in the CPU, and now it starts a real transaction over the HB or the XI lines. Thank you. I hope it was clear enough.
So there is a question. There is a question, Elihai, I don't know if you are seeing it, but there is a question by Itamar Nitzan. What do you do for gate level simulation? Elihai, can you hear me?
Yes, I'm just here. I'm looking on the first question was from
Oh, okay. There is another question before. So if you are looking at it, you want to address?
Okay. Okay. So let's start for the gate level. The gate level, actually, we tend to run pure C code. Our approach is, because our SOC, our system on chips, is coming higher and higher by size. The size is coming higher and higher. So our recent approach is to run only C code. So no test, only C code, and no test, almost no test bench existed. And all kind of loopback tests and self-checking tests with the C code. But of course, when we had smaller SOC, this approach could also apply to gate level. The only thing is that you need to keep the buffers over the part that you want to override, like the HB bus. You need to keep it by the same name in order for the synthesis not to integrate it or bypass it or vanish it.
So there was another.
Yes, I will go to the head of the. Do you have issue with the resulting ASM? It's cycle efficient in terms of what? Okay, the question from Elhanan, do you have an issue that the resulting ASM, or C in my case, is cycle inefficient? What do you mean by cycle inefficient?
So he can't respond now. So let's defer. There's another question, which is a clarification question by Nishant Pani. What exactly do you mean by random content? Do you mean some C program that can compile and run on the platform?
What I mean, I can go to the relevant slide. Do you see the slide, or do you see the chat window?
No, we see the slides too.
Oh, great. Okay, here what I mean by random content is that I just have a few structure of system Verilog arrays in this case, and this is a virtual sequence. So I randomize it, and I get, let's say for simplicity, I get 1,000 addresses and 1,000 data to write to via the HB. and then I just create, using the second part, I create a C code that's matching this. So here we can see, let's say the F write is actually, I'm writing the C code itself. So read value equals to volatile. This means I want to read from this address, and then of course compare it to the expected value. This is what I mean by random content. It's I just random a scenario. So it's random scenario, and then I'm converting it to C code. So now I have random C code content. This is what I mean. I hope this was clear enough.
Yeah, so Elihai, thank you for the presentation. We'll stop here. There is another question about, I understand that you got some private questions that we'll come back to them. And there is a question by Srini about why not PSS for this project. I think it's a great topic. Let's get back to this in the Q&A
Sure.
session. Okay.
Thank you.
Thank you, Elihai. I don't know. Well, first of all, there is a button for reactions, I believe, at Zoom, so you can applaud by reactions. And in any case, let me share my screen back. And let me share my screen. And okay, can you see Elihai on my screen? Elihai, can you see yourself? Yes, you can.
Yes, yes.
Okay, so with that, we're gonna try to do our first poll. As I said, sometimes it works with Zoom, sometimes it doesn't, so I hope it works. So I'm asking you, how did you like Elihai's presentation? 5 is great, 1 is less interesting, less relevant for you. And oh, wait, I need to launch the polling. Yes, so you should have it. So you guys, if you guys can vote it. Elihai, I'll tell you afterwards too. I'll wait a few more seconds. Okay. Elihai, I'll share with you afterwards, but overall, great presentation. And we're gonna move on. We're gonna move to Salvatore Rosselli's presentation, single generated UVM register model to handle multiple DUT configurations. Salvatore joined ST Micro in 2011, initially as a digital design engineer. Since 2018, he has worked as a senior verification engineer and verification leader for the microcontroller division at ST Micro, in charge of the functional verification of some peripherals for both the MPU and the MCU lines under the STM32 very successful brand. He is an author of patents and trade secrets in the fields of design testability, multi-synchronous digital designs, and reconfigurable computing systems. This paper actually was presented at DVCon US that happened actually just a month ago, but it looks like it was a long time ago. With that, let me make you a host, Salvatore, so you can share. Let me unmute you and make you a host so you
Hello?
can.
Can you hear me?
So you can share your screen. We can see you well. If you want to
hear me
share
too?
if you want to share your presentation.
Yes.
So try, Salvatore, go to display settings.
Yes, I believe it's the second monitor that is.
Okay.
Me, I remove it. Maybe it's better now?
No.
Not
We
yet.
don't have your, no, we don't have your presentation.
Wait.
You can go to what you did before. Okay, great.
Okay, okay. So this presentation is about creating a single generated UVM register model to handle multiple DUT configurations. So in the context of digital IPs, where large code reuse, extensive code reuse is becoming more and more a significant challenge, and register verification is more and more a hot topic. Sorry, I have something. Okay. So parametric designs are today a common reality because parameters are a simple yet powerful way to facilitate code reuse and flexibility. And today, the permutation of valid RTL parameters for a given IP is becoming very large, and we always have many DUT configurations, especially in a context like the one of microcontrollers, where reusing IPs across different projects within the same family is a challenging task and is very relevant for our business. So today, an important part of verification is the modeling of the DUT's register. Today, it is really a must because registers represent the way in which the IP interacts with the software. Verifying registers is one of the most common and relevant tasks in RTL verification. But parameters also have a deep impact on registers. So we'll see in this presentation how to make a model that is able to cope with parameters without really writing it, but instead by generating it and by making a single model capable of handling really a lot, ideally all configurations in the same digital IP. So parameters modify both the structure and the behavior of the registers. The structures of the register implies the existence of a field, whether it is reserved or not, and the positions and the reset values of each individual field within the register. The behavior of the register involves the possibility to read or write to the register and the location, I mean the offset of the register within the address map. So for example, according to a parameter value, a register can be entirely reserved, so it will always be read as 0 and will not be written. And experienced UVM users will notice that this distinction between the structure and the behavior of the registers matches the arguments of the configure method in the UVM reg field and the addReg method in the UVM reg map. So it's not actually a distinction that is new or novel in the world of dynamic verification. In the state of the art today, the basic building block is the industry standard-based classes for system Verilog under the UVM library. Moreover, today, several techniques and even full-fledged tools already exist that are capable to describe multiple register configurations to create UVM-compliant system Verilog classes, starting from high-level languages or descriptions. and in this way to handle the effects of parameters on the register model structure and behavior. Yet, the generated classes today are created in a way that makes for a separate set of register model classes for each configuration. So we indeed have multiple models, one for each configuration. Each group is really a subset of all possible registers, fields, and cover groups. So in the traditional flow, we start with the parameters. The parameters described with the range is a configuration space. And with a high-level language or description, we feed a generation script that generates an individual register model for each configuration. All these classes are not compatible. So you can use the generated classes only for that configuration, but not for another one. Indeed, this mechanism of generating classes is very well suited for an environment that aims at verifying a single configuration. So you generate the configurations you need, you select the proper one, you use the parameters to compile this register model, and you plug it in your environment in a seamless way. Problem is that this way of making an environment only creates a limited environment that can verify a single configuration. This is not the real power of parametric verification. In a parametric environment, what is really powerful is the capability of handling several different configurations in the same UVM piece of code. So somehow we have a big set of register models. We need to select one of them and to make this model interact with our parametric environment. To do so, and to be able to instantiate any of the several register models we have, we need some integration strategy and some piece of adaptation code. So somehow we need to create a class hierarchy or some interfaces or building classes that allow our parametric environment to call some accessory methods of the register model and to get a meaningful value, even a dummy value, for all the possibilities. Because the individual register model for the specific configuration we are running at a certain time, at a given time, does not contain all the registers, the fields, and the cover groups. So if we just plug the register model as it is, we'll for sure end up with missing fields, null pointers, and missing methods, and so on. So there's a big effort involved on the side of the verification engineers to deploy this integration strategy that allows their generated models to interact with an environment that is capable of supporting multiple configurations at the same time. In the traditional flow at a glance, is indeed more complex than it looks, because from the parameters, yes, we produce the parametric register view with the high language, and yes, the script generates our register model. But then it's on the verification engineer to make an integration strategy and which drives the adaptation code for our register model to be actually instantiated in the parametric environment. So in this paper, we try to find a way to generate a single register model that is capable of handling all the configurations at the same time. So this register model needs to contain all the possible fields, registers, and cover groups in the same piece of code without resorting to macros or complex class hierarchies. And we'll see how to do this in the following slides. So the flow is actually quite simple. We start with the parameters, and as before, they represent a configuration space. Then we provide a high-level description of this parametric configuration space, which we call the master configuration. And through a script, we generate a register model. But the difference is that the register model is unique and unifies all the possible configurations of our IP. The script to generate this register model is provided in the appendix of the paper, and we'll see how to create this master configuration, even for the cases where different registers make for impossible or incompatible configurations, because the mechanism is capable of handling that too. So the flow is a lot simpler, much simpler than the traditional one. We have a single description, which is the master configuration. We feed the script that is ready to use. We get the register model classes, which are suitable for all the configurations at the same time. So we can already instantiate this model seamlessly in our parametric environment and make it interact with the environment itself in a seamless way, regardless of the configuration for which we compiled our RTL and environment. The knack of this mechanism is a configurator object that is instantiated within the parametric environment that uses the parameter to configure the register model. The configurator is ready to use again, so we need to write no code in any way, and we need no adaptation code to make our parametric environment interface with the register model. So everything in this flow is actually reusable. We do not need to create code from scratch. We do not need to make adaptation layers that are impossible to reuse in the future project or in a different design with different specification. So how do we use the register model? Before digging in the implementation, let's see how to use it. So I don't want to know how it is done. Let's see how we want to use it. So in the build phase of our test, we instantiate the register configurator object, which is provided within a library. We'll see later how it is done. And we plug a component, for example, the environment, as the scope of this register configurator. We'll see why this object needs a scope, but in reality, it's just a reference to an existing component. So in this case, it's the environment. And then we use the configuration object before instantiating the register model. This is an important point. We'll see why, but it's important that the configurator object is instantiated and used before the register model. In this example, we use the register configurator to set the register myreg1 reserved. And we provide some values for the two fields, myfield1, myfield2, to set the reserved values. So actually what we are doing, we are stating that myreg1 cannot be written anymore in this configuration because my parameter is equal to my value 0. And so the register is removed. It will always read thus the reserved values that we provided in this associative array. The register model can now be instantiated And the way the register model is instantiated is actually the same as with the traditional UVM registers, except for the set scope line, which sets the scope of the register model. It's important that the UVM component that we pass to this method is the same as the one we plugged in the configurator object. And we'll see why, but the real point to understand at this stage is that this component makes for the association between the register model and the configuration object. The UVM component we pass needs to have no particular features or belong to any particular class. We only need to provide a hierarchy in our environment. To use the script to generate our register model, the user needs to provide the master configuration. The master configuration is the equivalent of the high-level description of the traditional techniques. It's actually a special register description that contains all the possible registers, fields, and cover groups of the DUT. It's important to notice that this master configuration is not necessarily a real configuration. It doesn't really need to exist in the configuration space. So you might have registers that are incompatible among them. You can have overlapping fields. You can have inconsistent cover groups. It doesn't really matter at this stage. Registers, fields, and cover groups in the master configuration only need to be defined. The content does not need to carry any functional meaning whatsoever. So you can write dummy addresses, non-existent positions, inconsistent reset values, dummy values of any kind. It's not really important as far as if two registers can exist, even not at the same time, both registers need to be present in the master configuration. So to make an example, this is a very simple master configuration that contains only two registers, A-reg and B-reg. A-reg is a read-write register located at address 0, which defaults, means resets, at value 0. It contains three fields, A1 field, A2 field, A3 field. And they are located at address 15, at position 15, 8, and 19 respectively. B-reg is read-write 2 and is located at the same address 0. So the two registers can never exist at the same time, probably. It doesn't really matter. 0 can even be a dummy value that does not match the reality. This register results to value 1, 2, 3, and the fields that it contains are B1 field, B2 field, B3 field, B4 field that are located at different bits of the register. And you can see that some of them are 1 bit long, some others are 2 bits long, and so on. We chose YML as the format for this file because it is human readable, and so you can read and write manually, and it's easy to modify. But also because many programming languages already have full-fledged parsers and dumpers for this format because it's standard. So you can even generate the master configuration from another script or some other sources of information. And this is actually what we do in ST. So now let's dig in the implementation. So we need to find a way to describe the registers. So first thing is that we provide an abstract class that we call myAbstractReg, extending from UVM reg. This class is actually what you see in the screen. It's ready to use and customizable. You can add your own content, and all the registers will get this content. So methods that you want all your registers to share can be added here. And you have an empty build function, and we'll see how it's used and overridden later. And the set scope functions that we used in the previous slides. So it's really not much code. The important thing to notice is that we add a reference to a component, which is what is really the added content in this virtual class. The script will be fed with the master configuration and will generate all our registers. All the registers will be generated as an extension of the abstract class of the previous slide, one class for each register. Users are not supposed to write or modify this class manually. This is all generated code. This is quite useful because in case the specification changes, the user can just regenerate the code and he only needs to update the master configuration. So how are these registers made? So they actually contain coverage constructors and registers fields that are generated by the script, and the build function, which is overridden from the virtual class. The build function is actually the build function is actually made as in this slide. So this function, this method creates the fields within the register and adds a block that we'll see in the next slide that sets the actual values for each individual field. So you remember that the content of the master configuration was dummy. Here is where the real values are taken. How? The build method actually looks for some particular objects in the configuration database that are named after the registers and the fields, and retrieves from these objects from the scope that was the linking point between the register model and the configurator, and uses these register field objects to override every field or every argument of the configure function. So if the register field configuration object has the attribute change width, it will override the width value with the content of this configuration object. In this way, we are able to rebuild entirely the structure of the register for the given configuration. We'll see how the register field object arrives in the UVM config database, but of course I can anticipate that this is the job of the register configurator object that was instantiated in the test. So now we have several registers we make for an address map, so a UVM reg block. Again, we create a virtual class that extends from the traditional UVM reg block. We plug a scope because we will do exactly the same thing as for the register actually. So the set scope function is provided too, an empty build method is provided too, and the user can add any custom content that the user wants the register blocks to share. For example, a search method that looks for a register by name or any other capability. And the script will generate a register block class with coverage constructors and registers as for the individual registers. And the build function is generated by the script as well. We'll see in the next slide what it does. But again, users are not supposed to modify this piece of code. This is all generated by the script. And what is inside the register block is actually mainly the build function, which instantiates the registers, calls the build methods of the registers, which are the ones we saw in the slides that preceded, and the configure methods of the reg1 and reg2 and all the registers in our register map. Then we configure my reg1 and my reg2 in the address map with the real behavior. The mechanism is the same. We look for a particular configuration object in the scope, in the intended scope of the UVM configuration database, and we use the content of this object to override the offset and the access privileges of this register. In this way, we have overridden both the structure of the individual registers and the behavior of the registers within the address map. The result is that we completely restructured the register model according to the values of the parameters, because the objects contained in the UVM configuration database are actually simple descriptions that contain a change underscore field. For example, here is the change access, so the direction read only, write only, read write, and the new access privilege to override the one provided by default by the master configuration. So the master configuration sets a default that is entirely overridden by these objects. So here is the register field configuration, which on top of the access privilege adds a reset value, the width of the field, the least significant and the least significant bit. So by using the set width, set LSB, and set reset value methods, we can override every little argument of the configure function. And the same applies for the offset in the address map. So overall, these configuration objects are set by the register configurator class that we instantiated in the test. It's important that we instantiate it before the register model, because what we are actually doing is setting some objects in the configuration database. So for the register model to retrieve them during the build phase, being the build phase top down, we need the register configurator to be instantiated as the first thing. And what the register configurator actually does is exposing some methods that actually just set some configuration objects in the UVM config DB using the scope of the component for the register model to retrieve them and reconfigure itself. This is, for instance, an example of the reserve reg method that takes the name of the register as the first input and an associative array of the fields with the reset values. So what the method actually does is scanning the list one field after the other, applying the reset value to each field, setting each individual field as read-only, and setting the configuration object in the configuration database, which is what that set field CFG does. So it's actually just UVM DB UVM config DB set. And then we set the all register read-only. So to conclude, this paper proposes a configurable register model that lets the user regenerate all the configurations entirely when the specification changes with just the pressure of a button. It provides a seamless interface towards the parametric verification environment without any need for adaptation code or complex integration strategies, or any very high level of nesting and class hierarchies. The register structure is described in a simple format, which is YML, which is very simple both to read and write by hand, but also to generate from a piece of software or a script. The paper contains in its appending a conversion scripts that takes the master configuration and generates the UVM classes automatically, decoupling the parameterization of the registers from the register classing themselves. So we make the parameterization in the configuration objects and the description of the register classes in the generated code itself. You will also notice that the coverage model we define in this way is a single one. It's unified. It contains each and every field for all possible configurations in our digital IP. And this composite coverage model is quite interesting because it creates a first attempt of creating multi-configuration coverage collection, which is today a hot topic and still mostly unexplored. And for any question, please, you are very welcome.
So thank you very much, Salvatore. I want to, because some people need to go, I want to move on, and people that have questions will stay a little bit longer. So I just want to ask you for your opinion about Salvatore's presentation.
Okay. I can answer to. Do you want me to answer to the question?
So I just want to ask another question to everyone, and then we can stay to answer to the different questions. And there are quite a few questions, which is great. I want actually to ask, because some people need to leave, so I want to ask people. Would you like to have, since it's the first time we're doing something like that, would you like to have additional meetups like this once a month, once a quarter, or not interested? So, oh, sorry, I need to launch. So now I launched it. So if you can give us the feedback on that. Okay, so we don't have, okay. Okay, so we're gonna finish, last calls. Okay, let me see if I can, if you can see, can you see the results? Yeah, so you can see the results, I guess. So that's the results we got, which is a good indication that was valuable. So let me just, in taking in mind that we're going to have additional meetups in the future, if you have an idea, so a topic you want to present, please contact us. We're going to go to Q&A, and I'm gonna, Srini, you had two questions, so I'm gonna open your mic and you can ask the questions. Then Ivana, you can ask your question after that, and then we can open to other questions as well. So Srini,
yep,
you're
thank
welcome
you.
to ask.
Yeah, thank you. Hi, this is a good presentation. Thank you. And I believe I probably missed it at DBCon. So it was definitely a good opportunity for me to look at the content. Thank you. And one simple question that I had for the presenter is you showed us the set coverage with the UVM CVR all, which basically says cover everything in my register model. And in my personal opinion, in my personal experience with larger designs, this tends to slow down a lot with the value addition coming from it being very, very less. So I was just curious, is that really something you use in your designs, or is that just shown on the slide?
And before you answer, if whoever can show his camera, can open his camera so we can see some faces, that will be nice.
I agree with you. With big designs, it's not really feasible. The reason why I put that in the slide was just to show an example and to show that the model is complete and can provide all the aspects of the coverage. But of course, a trade-off in terms of performance and completeness is on the verification engineer. Anyway, this is tunable at the top level as you would normally with any register model. So no difference here. I hope I answered your questions as you expected. And
Srini, okay with you? Okay, so let's, I don't know what happened to Srini, but so Ivana, you wanted to ask a question. Again, whoever wants to or can open his camera so we can see some faces, that would be great. We can't hear you, Ivana, for some reason.
Do you hear me now?
Yes, now we hear you.
Great.
And so the question is to Elihai or to Salvatore?
Yes, I have a question for Elihai. It's regarding generating this random content for C tests. What UVM phase has been actually used for loading it? And
You're muted, Elihai. Wait, I need to open you. Sorry. Now.
Okay, actually,
no, yeah.
You mean which UVM phase?
I don't think we are hearing you well for some reason.
Now? Can you hear me now?
Let's try.
Okay.
You're muted.
And now?
Yeah, okay, let's try now. Now we can hear you.
Now you can hear me?
Yeah.
Okay, you mean which UVM phase I'm creating the content? Yes, right. Actually, it's although it's the run phase of the simulation of the UVM, the CPU is still on. It can be on reset or on halt. So the simulation started, and we are out of reset. All the rest of the stock is out of reset, but the CPU. So and then we can randomize the content, create the C code, and then translate it to hex files, and then load it to the CPU, and only then take the CPU out of reset or out of halt. So the answer is that it actually can be no issue, can be the run phase, as long as the CPU is still halted and didn't start to fetch new instructions.
So Ivana, you're muted. But now everyone that wants to speak can unmute. You know, whoever wants to speak can unmute himself now, and so Ivana, yeah, you want to say something?
Just to confirm that everything can be done in a run phase.
Yes, no issue.
Okay, thanks. Thanks for the answer and great presentation.
Thank you.
Thank you, Ivana. And Srini, I realized that I muted you before, so now you should be able to speak.
Yeah, hi. So this is to the previous presentation. You can hear me?
Yes.
Okay, great. So it's really a good presentation. I wanted to understand, not as a must, but did you explore using portable stimulus for the sort of challenges that you have described when it comes to embedded processors? Thank you.
Actually, I started to look on PSS after I completed this method. What I find is that it has some common links, but PSS is more heavy approach and requires different tools and probably long integration, probably weeks. And what I presented here is already, you can implement it already in your existing test bench. So, and second of all, I didn't, if portable stimulus is the essence here is you can port it, but here I didn't want to port it anywhere. I just wanted it to be in the simulation. So there was no real need to use this new method for the new PSS flow, because the real advantage there is I don't really need to use it at this point.
Thank you.
Peter Shaggy, you wanted to ask something?
Yeah, so I want to ask from Salvatore whether you have some solution also for the stimulus side, for the sequence side, so handling different register map configurations. So for example, in one case you have one register, the register A, and in the second DUT configuration that register is missing or looks another way, so with other fields and such. So, but you have probably the same config sequence. So can you handle it somehow?
Salvatore, you are okay.
Yes. Okay, so two points here. The first one is if you use the write mirror methods from UVM Reg, you can for sure, because you can use you already have an updated mirror of your register, and you can read and write accordingly. If you don't use that, which is often the case, especially if you have complex register mechanisms, and then what we do on our side is creating a sequence that covers the largest case, the case that covers most of the conditions, because everything that, for example, is reserved needs to behave as reserved. So it means that we can verify a register even if it's missing, and the expected behavior is the one of a missing register. So I reserve the read-only register with a predefined content. In case of registers that look different, you can do it depending on the way the registers differ. So if they are completely different, so they have nothing in common, you can treat them as two different registers that share the same address. So at a given time, you will have one and not the other. Or otherwise, if they are quite similar, for example, it's just a field that increases or decreases its size or changes its capability, you just make a children class of your sequence to handle that differently and use the UVM factory to make the trick. I hope I answered your question.
Yeah, so actually then you have to somehow have different sequence configurations which are not generated by scripts. So you generate the register side by scripts, and you have to align your sequence side somehow manually.
Yes, today I only generate the register sequence. So just a simple register test that tries and writes and reads all the registers in a random order. That's for sure. But if you want a complex virtual sequence that handles the full programming, etc., in our case, because we mostly deal with software configurable register, because we work in the microcontroller field. In our case, this is a wider task that involves a lot of other stuff. So we can just simply make it automatically and push button. It's more complex than that. But theoretically speaking, you can automatize the sequences because you have a register that contains everything. So you can ask the register model for what is there and what is missing. You can make your environment talk to the register model.
Okay, thanks.
Welcome.
I have a question for Salvatore.
Okay.
Can you hear me, Salvatore?
Yes.
Hi, how are you?
Hi.
Wanted to ask regarding you're doing your changes to the RAL class post-process after the generation of the automatic scripts, right?
Yes.
So we have some big projects that the RAL class itself reaches above 1 million lines.
Okay.
So this is hard for even now it's hard for the compiler. And you presented your part, so it's adding more lines to each field and in each block and each register, so it can be bigger and bigger. Did you see any performance issues? Did you deal with such RAL?
No, I didn't have performance issues because consider that all the code that is added is resolved in the build phase. So it's run just once while the register model is being created. So you don't poll that code several times. You just run it once, then the register model is defined, and it takes more or less the same memory as it would otherwise. The only difference is in the coverage, as Srini pointed out before, because the coverage model is much larger, and that is probably the only critical point with coverage, but that depends on what you want to collect. And of course, most tools offer ways to disable selectively. So it's something that can be dealt with in case you have a very, very large register structure.
Okay, thank you.
Welcome.
So I don't know if there are additional questions, and people can stay on the line and talk to each other. But because some people need to go, I just want to wish all the attendants in Israel. In 2 days, we are going into the Passover, the Pesach holiday in Israel. So I wanted to wish all the guys in Israel, all the people that commemorate Pesach, a happy Pesach. And for all the people, since we have a very international crowd today. So people, you know, and different people commemorate different holidays in different places, different times. So, but overall, wishing all a happy spring, that this spring will bring us good health that we need as a world community, and prosperity and peace of mind, and that we can have additional opportunities to share knowledge as we had today. Again, whoever needs to go is, you know, welcome to go. People that want to be on the line and continue to discuss, you're very welcome to. Thank you very much.